right. Hello all. Good afternoon. I'm Adel Bibi, and this is a joint work with Modar Alfadly and Ghanem from KAUST, Saudi Arabia. And I'm going to talk to you today about some analytical expressions that can be used to analyze deep networks under Gaussian inputs. All right, so there is an uncouth behavior that we have been experiencing the past few years in which it seems that it is easy for people to actually generate adversarial attacks. And by that I mean, given a network and given an input image, let's say the network is doing classification, is doing very well in classifying that panda correctly. It seems that it's somewhat, there are several approaches in which you can generate a small imperceptible noise that once added to panda, all of a sudden the classifier goes crazy and classifies this panda as gibbon. So there are lots of works on this, like in non-targeted attacks and target pixel attacks, and people have also shown that there are methods where you can just corrupt a single pixel and that will completely destroy the classifier's performance. Even more interestingly, people have also shown last CVPR that there exist these deterministic samples that once you add them to any input image, you can just completely destroy the classifier's performance. And this does not necessarily have to be sampled from some distribution. And there are also empirical studies that shows that these samples are agnostic from the network architecture as well. So you can take the same exact input image, apply it to any input image to any classifier you wish, and you just destroy the classifier's performance. So this, intrigued so many questions on why does this actually happen. I'll try to tackle this problem from a slightly simpler approach, and maybe this approach will provide us with some mathematical expressions that help us understand what's really going on there. So we'll start with the assumption that the network is actually made up of nonlinear activations, and these nonlinear activations are precisely ReLUs, in order to force the networks to have this piecewise linear sort of structure. So the simple question that one would ask is, assume that you have a noise sample from some distribution G. This network is nothing but a function that generates some new random variable that has a new distribution. And the simple question is, what is this PDF distribution? And if we cannot find a closed form expression for that, can we find closed form expressions for the output mean and output variance for such a network? Now, it seems that even under simple assumptions like having Gaussian input at the input level of the network, which is one of the most stable distributions that we know, we cannot actually get a closed form expression for arbitrarily deep network. And we particularly believe that there might not even exist such a solution with respect to some elementary functions. So what can we do there? Because the problem seems just too difficult. One way to do it is just to look at bottom-up approach. And you ask a simple question. You say, for how many layers can I derive these closed form expressions? And we were successful to some extent to derive these expressions for a very small network that seems to be practically useless, right? Just affine, ReLU, and affine, right? And so it's given in the expressions g of x, and then x is assumed to be Gaussian, right, with some mean. And that mean could be any arbitrary image. Great. So, so the paper structure is followed that we present two theorems. The first theorem would discuss about what is the expression of that mean for this small particular network. And the second theorem will talk about how would we derive the variance. So with simple analysis with probability theory, one could derive the expectation of gi of x, where I is just simply the ith function at the output level. Great. Now, the variance is slightly more trickier, and we represent it with the following technical lemma. So there are other results. I'll just keep them to the poster session. So what this lemma tells us is the following. Assuming you have some nonlinear map psi, and under the very mild assumption of this function psi, which in this case would be our small function, which is max linear, ReLU linear, now you can relate directly with an inequality the expectation of this psi under Gaussian assumption with respect to the covariance parameters of the matrix. And that is exactly equal to the expectation of that function with respect to the input variables. So you can think about this as a differential equation, and once you are able to solve it, you have access to your expectation of psi of x. Now, why do we need it to be piecewise linear from the get-go? It is because you can imagine psi of x. You can think about a ReLU. If you take second derivative of it, you get Dirac delta functions, and the right-hand side becomes trivial to evaluate. Right, so I have to emphasize now that this is a result that is extended from a paper published in the Transaction for Information Theory by Roper Price, and to our surprise, it was published in 1958. And these results just keep popping up to be extremely useful in the deep learning community. So I mean, with a couple of other few results, now we can actually figure out what the closed form solution for the second moment of that small network is given in this form. Now, this is overwhelming from the slides, but we can parse it at the poster session later down there. All right, so great. So what do we have now? Practically useless network where we have some expression for it, where we have expressions for the mean and the variance, right? Great. But how is that useful? Okay, so now what I'm going to talk about is how would we extend arbitrarily sized networks into this particular form, and the idea is very simple. So we start from a network of your favorite choice, train, so we don't do any trainings, and what you do next is say, okay, so let's say this network has D output function, so it has D classes of some form, and all you do is you select a ReLU of your favorite ReLU in that network, right? And then what you do is simply you perform what we call a two-stage linearization. You linearize everything after the ReLU, and you linearize everything before the ReLU. And that will precisely give you the structure we're looking for, where the linear parameters are described by the Jacobians of those two linearizations. So now what we'd like to do is use these expressions that we know for the smaller network in order to infer something about the bigger network. Okay? So first of all, I will bore you with some tightness verifications before going to some of the exciting experiments at the far end that relates to some nice applications. All right, so a simple experiment one can do is Monte Carlo estimates of these expressions is basically you generate any random network, fully connected or convolutional if you wish, and we have varied the number of layers on depth layers on that, and we compared the analytical expressions with Monte Carlo estimate for the mean and variance, and these plots you see the slope, which is 1.0, so the closer it is to 1, the better the performance in general. Great. So another question might be is, okay, fine, so the ratios or slopes are close to 1, but are they, do they actually preserve the ordering score in networks? So in classification, sometimes we don't really care about the exact score, but we care about the ordering in order to infer the class label. And this, as we did this experiment, for example, on AlexNet, where for the first bar you see top 1 accuracy, you see how much these expressions predict the location of the maximum score across the complete validation set. And it does it with a 98% accuracy. And we do it for a top 5 accuracy, which reaches about 80%. Now, the metric we're using is very, very strict. And that's why 80%, in fact, is very good. Okay, so there are plenty of other experiments that I don't have time nor space to present them about tightness on LeNet, what choice of ReLU do you have to make for better performance. Linearization cannot not necessarily have to be done with every single input. You can also now visualize, you can now plot these expressions as a varying variance level at the input, which you see in the x-axis, and see how these logics interact with each other. Okay, that's for the poster session. So let's do some nice experiments. So the first experiment is, can we infer something about the sensitivity of the network using the expressions directly? So think about your covariance matrix. If you made it sparse with except for few pixel locations, those will be exactly the pixel locations that will be corrupted in your image, right? So what we're going to do is basically we take an image, let's say a 1 in this case, and we're going to evaluate the expressions, the output mean, for every single class label under sparse covariance matrices, and the non-zero locations of these sparse covariances are precisely the pixels that we want to corrupt. And we simply look if the maximum score existed in somewhere other than the correct class label, and this is what you see in red. The red location are locations predicted that once you add noise at this location, it will flip the class label, and completely using no forward passes, just evaluation through the expressions. And this is what you see with the class label 1. That you see red regions at the top part, and this makes sense because a 1 in that case would look like a 7, and so on and so forth. Great. So the next experiment would be something even nicer, which is you can ask a different question. You say, okay, fine, we have these expressions for the mean and variance. Now, can we optimize for the input mean and input covariance of the Gaussian matrix such that if I have an input that is a 9, the output classification score for it should be something else. And this is what we call targeted adversarial attack. So I want the network to classify all 9s on average as a 2 or 3 or a 4 and so on. So what we do is simply we maximize the difference between the expectation of the correct class label with respect to all other class labels. So J here is the incorrect class label, and we want to make that as high as possible. And again, so E is the expectation where the mean is the image 9. So once you optimize that, of course, you have to put some boundaries on what the variance should be, because you don't want this to go to infinity and so on. So you can actually now design a distribution parameters in which once I sample from this distribution, on average, we're going to fool the network to the particular targeted class. Something even more interesting you can do is to say, okay, I don't care about targeted class, but rather all I care about is fooling the network to any arbitrary class with alpha % support. It means I will select random pixels in the image. I say, okay, those random pixels I want to corrupt. I just want the distribution parameters, Gaussian distribution parameters at the input, such that once I sample from that distribution, on average, I will flip the class core of the image. And you formulated something very similar to before, and we have experiments on MNest and ImageNet as well, where, for example, if we corrupt 4% of the pixels in MNest, we fool it. If we corrupt about 2% of the ImageNet experiments, we also fool the network as well. All right, so future work, obviously there are so many things that can be done. We can analyze different types of adversarial attacks where the noise is particularly structured in a particular location. We can maybe use these expressions as regularizers. For example, you want to minimize the output variance of the network if it were subjected to some certain types of noise. And maybe even derive deeper expressions for deeper networks and the different noise distributions. So please come see us at poster H19, and there is a code for this on TensorFlow, PyTorch, and MATLAB, and this is the GitHub link. Thank you very much.
To remind, there are 2 microphones, and if you have a question, please come forward and ask it. So I have a question. Have you ever actually tried to harness adversarial examples, and whether this procedure works better for improving the robustness of the network compared to previous approaches?
Okay, so are you asking about if we generate these samples and use them for robust training?
Yeah.
Okay. So one experiment I did not mention is that these expressions were also useful to predict the fooling rate of other adversarial examples, but of course we don't have time for that. But we also have a submission to ECCV where we actually use these expressions as a direct embedded regularizers in the training to better improve the robustness of the method.
Okay, I guess the last session makes an impact. Okay, let's thank the speaker again.